Okay, so properties are going to be similar in a given column. So when you look at the periodic table, if you don't have one open already, open it up in another tab on your computer or your phone or whatever so that you can flip back and forth because we will use that a lot today. But arsenic and antimony, SB is antimony. I don't know what that Latin word for antimony is. Anyway, those are in the same column, so we call those families. And we don't really know why they have the same properties yet. We just know that that's how the periodic table was organized. Okay? And then charges are also based on the columns on the periodic table. So if you scroll up in the notes in this page, that's where we looked at what charges form when a compound forms an ionic compound. So charges come from losing or gaining electrons, but that only happens when we're talking about ionic compound formation. So in covalent compounds, which is a different type of bonding, we haven't talked about it yet, so don't stress if you're, like, what is she talking about? In the next chapter, we'll talk about the different types of bonding, but there are lots of other bonding where you don't have a loss or gain of electrons. If you remember from high school, we call it electron sharing rather than electrons being lost or gained or transferred. Okay. If you have something where they're lost or gained, though, these are the charges that'll form based on the column. So just do it visually, have a periodic table and say +1, +2. You skip over the transition metals because those ones can do multiple charges. +3, blank, -3, -2, -1. And then the noble gases, we don't talk about those because they certainly won't bond in ionic compounds. So they will not gain or lose electrons. Okay? All right, so today we're going to focus a lot on the masses specifically that are listed in the periodic table. So scrolling up to the one that we have on the exam equation sheet, we need to talk about where these masses that are listed under the elements, where those numbers come from, and then also how to use them, okay? So when we talked about isotopes, we said that we talk about them as having a mass number, so like carbon-12 or carbon-13, but that number isn't the exact mass of that thing. It's going to be close to 12 or 13, but we round it when we're doing it in a name because we don't want to say like carbon 13.004 or something. That would be annoying to have to do that, okay? So those are rounded. So initially when people look at the periodic table, they think, oh, well, these must just be those unrounded numbers. And that's not the whole story. So what these numbers on the periodic table, what these masses are, is actually what we call a weighted average of all of the different isotopes that contribute to a particular element. So for example, the carbon one that we looked at, carbon is mostly carbon-12 and carbon-13 with a very small amount, tiny amount of carbon-14, okay? And I'm going to scroll down so don't get lost as I scroll. Okay, so if you want to come to this slide, it's after those practice problems. We're at the practice problems. I went up to the periodic table, and now I'm coming back down. So in carbon, 98.93% of the carbon is carbon-12. Okay, so the isotope that has 6 protons and 6 neutrons. And then 1.07% is carbon-13. So 6 protons, 7 neutrons. And then the carbon-14, 6 protons, 8 neutrons, is so small that this question just kind of pretended like it didn't exist. Okay? So there is carbon-14. It's probably like 0.00 something percent. So to simplify the question, they just got rid of it. Okay, so if people think about a normal average, like if we talk about, let's just, calculate the average of something, usually we just take some numbers, we add them together, and then we divide by however many numbers we had, right? So if we were to do a straight average of these two masses, we would do, so this is just like, I'm going to call it regular average. We would take 12.000, however many zeros that is, plus 13, and we would divide by 2. Right? That is like standard form of doing averages. That's going to get us close to 12.5. I'll give you an exact number. 12 plus 13.0034 divided by 2. Oops, need a little parentheses there. 12.5017. Okay, that makes sense. If you have 12 and 13 and you take the average, you should expect it to be 12.5. When we look at the periodic table, though, the periodic table says 12.01, so that must not be the whole story. What we want to do is a weighted average, which accounts for the fact that these guys are not equal proportions. One has 98% or almost 99%, and one only has 1% contribution. So the way that you do a weighted average is you take the percent in decimal form. So I'll say percent as decimal, and you times that by the mass. So we'll say of isotope 1, I'm trying to make this like generic. And then you would add the same thing for the other isotope. Percentage as a decimal times the mass of isotope 2. And if you had more isotopes, you could continue on with however many you had. As long as they have their percentages adding up to 100%, you can use as many isotopes as you're given. Okay, so how does this square with a regular average? Well, when you divide by 2, remember dividing by 2 is the same as multiplying by 1/2. So if I were to replace this, instead of saying divide by 2, I were to say 1/2 times this and 1/2 times that. What is 50% in decimal form? 0.5. What is 1/2? 0.5, okay? So when you do a regular average, what you're actually doing is like multiplying by equal percentages. So if it's 2 things, it's like you're multiplying by 50% each. Okay, so instead of multiplying by 50% each, we're going to multiply by what their actual percentages are. Okay, so we're going to do this one together, and then I'll let you guys do the chlorine one that's on the next page. But we're going to start this one, or do this one together. Okay, so in purple, I'm now doing the weighted average of carbon 12 and carbon 13. And hopefully, if we do it right, it should come out to be pretty close to carbon, or to 12, because most of that is carbon 12. And it should also match what's on the periodic table. Okay, so the the percentage as a decimal, so 0.9893 for carbon 12 with a mass of 12.0000 plus 1.07 as a decimal. You guys want a little math tutorial again real quick? What does per mean? I told you this a couple weeks ago. Divide. Yeah. So per cent. Anybody have any ideas what cent stands for? Century. 100. Yeah, 100. Okay. So 1.07 per cent divide by 100. That's what that means. So 1.07 divided by 100, or 0.0107. So the more you can turn math into like from words into math operations. The easier stuff like that is to understand. Okay, and then times the mass of that isotope. So that should be the calculation, not 50% of each, but now 98, 99 basically percent of one and 1% of the other. So go ahead and punch that in your calculator. And you should get something close to 12, but not exactly 12, because it's not all carbon 12. There's some carbon 13 in there as well. Okay, so when I plug this in, I get 12.0107. And periodic tables that have more significant figures, like if they go 3 beyond the decimal, will say carbon is 12.011. Ours says 12.01. So that matches with this calculation. Now, there is carbon 14. It's probably just such a small amount that it wouldn't change that answer. Okay, so why do we do this? Well, when we grab a chunk of carbon, so think charcoal, that's like the closest thing to pure carbon. If you were to take just any sample of carbon, it is likely to be pretty darn close to this distribution of isotopes. That's how isotopes work. They're not unequally distributed in the earth as much as you might think, because a lot of the elements that we're talking about got created so long ago in a concentrated place and then spread throughout the earth. So there's probably a fairly even distribution of isotopes in any one sample of carbon. Okay? All right, so when we do calculations, we're going to use that averaged value that's on the periodic table, and we're going to assume that that's good enough, and it probably is out to, I don't know, the thousandth place or something. It probably wouldn't make a difference if we knew exactly which isotope it was. Okay, so I want you guys to do one additional practice problem. Again, calculating a weighted average, in this case for chlorine, and double checking it, making sure it makes sense on the periodic table, both so that you know how to do this calculation, but also so that you understand where those numbers on the periodic table are coming from. Okay, so take a couple minutes, same thing as before. I should leave this, there you go, I'll leave this definition of a weighted average up there. We're doing it the same way that we did that previous problem. All right, so as you're finishing up, check your answer. Did anybody look it up on the periodic table yet? What is it? Go ahead.
35.45.
Perfect, 35.45. So really close to what this calculation comes out to be. So there is no one atom that weighs 35.45, right? It either weighs 34.97 or 36.97, depending on which isotope it is. But we're going to say, for our purposes, that one atom, and I'm going to write this as a conversion factor because we can use it that way, one atom of chlorine, we're going to say it's 35.45. The 4.6 is, part of the calculation. Our periodic table just says 4.5, so that's fine. But that's atomic mass units. So it's okay to say that because we're never actually going to isolate one atom anyway. We're going to isolate a bunch of them. And on average, each atom would weigh this amount. Okay, because it's going to be a mixture. Okay, so list of conversion factors. What have we added so far? So if you don't have your own list, it's time to make your own list because you're going to have an exam in 1 week. Okay, so you need to start with a physical list and in the next week incorporate that into a mental list so that you can refer back to it in your head when you're doing a problem on the exam. Okay, so we've done metric to metric. So knowing that there's 1,000 grams in a kilogram, that would be one example of that. English to metric, those are from the exam equation sheet. So 2.54 centimeters per inch. Density can be used as a conversion factor. So anytime you're given the density in grams per milliliter, you can use that as a conversion factor. And we have this additional one that any time you want, you can use the number on the periodic table. That's okay to use that even though it's a weighted average and there's not technically an atom that weighs that amount. We can use that number in AMU for every atom of that element. So let me just switch over to the periodic table real quick. There we go. So you'll notice that there's no unit listed on here. It just has the number. And there's a good reason for that we're going to talk about next. But when you look at chlorine, you can now add the conversion factor 35.45 AMU per 1 chlorine atom. Or 19 AMU per 1 fluorine atom. Okay, so that's another conversion factor we've added to our list. And then the rest of today, we get to add 2 more, okay? All right, I just said it's okay to do this, even though there's no chlorine atom that's 35.45, because we're never dealing with one individual atom. In fact, it is rare that we're even going to be dealing with 1 million atoms, or for that matter, 1 trillion atoms. That would still be a very small amount of a sample, okay? So to give you some perspective, carbon, which again, let's think charcoal. So crush up a piece of like charcoal that you would stick in a grill and scoop out 1 tablespoon of that. That is about 1 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm not going to have room. 16, 17, 18, 19, 20, 21, 22, about that, 23, 24. Yep, we'll call that good. So that's about how many atoms there are in 1 tablespoon of charcoal, carbon atoms specifically. We don't even have really a name for that. Like I think trillion, this is million, so that's billion, so trillion is here. So like we're like, a trillion is basically what we're talking about. It's a crazy big number, okay? So to make that easier, because like how often are you going to have smaller than a tablespoon worth of something? Maybe a teaspoon size, maybe even a quarter of a teaspoon, but now we're still in really, really big numbers. To make that easier to work with, there is an additional unit, and you've probably heard of this if you took high school chemistry, called the mole. Okay? Lots of times people are very stressed by this idea and they're like, I still don't understand. What is a mole? It literally is just a number. Okay? So when you say a mole of something, and it's ridiculous, but we abbreviate it MOL. It's just MOLE, but we use MOL. So don't try to use MOL for molecule because that means mole. So when you see mole, you're going to think this number, 6.022 times 10 to the 23rd. So 6 followed by 23 digits. What I wrote down was it was basically 10 followed by 23 digits. Okay, so when I say a dozen eggs, everybody knows I mean 12. It's very similar to that. It's what I call a named, oh yeah, I do have that under there, a named number. So it's a number that we give a particular name to. Dozen is the one that we most commonly use. 40 and 20 years ago, or not 20, wouldn't have been. 40 and what? What is it? 7? Okay, thank you. Obviously, I'm not a history buff. So score is 20. You can use that. It's most commonly used for years, but you can use it for other things. A gross is 144. I don't know what that comes from, but that's what a named number, gross, means 144. And we don't always talk in terms of even numbers, right? Like we might say 1 dozen or we might say 5 dozen. Like that's how eggs come at Costco, is in 5 dozen boxes. That's how we buy eggs in my house. We eat a lot of eggs. But you also might have like 1.5 dozen. And if I say 1.5 dozen, you guys probably know that I mean 18, right? What you did in your head there was 1.5 times dozen, which is 12, right? And that's how you got 18. You just did that in your head. So sometimes we might say 1.5 moles, and that would just be 1.5 times 6.022 times 10 to the 23rd. Okay, and we could technically use this number for anything. We could use it for eggs. It would just be such a ridiculous large amount of eggs, you know, the world would be nothing but eggs at that point. Because eggs are, you know, a normal sized thing. Atoms are not a normal sized thing. They are a teeny, 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 tiny thing. And so in order to talk about them we are on what we would call the macro scale. Atoms, we say they're on the atomic scale. And then when you start to get, you may have heard like nanoscale technology. That was like a big thing like 20 years ago. That's kind of like in the middle, or micro scale. That's kind of in the middle between the two. When things are on the atomic scale, we have to use really big numbers to talk about them to get it to a reasonable quantity on the macro scale, because we can't measure in teeny tiny amounts. So we use really big numbers to measure out small things. Whereas eggs, 12, that's plenty to measure that out. Generally, like things that are bigger than that, like, a loaf of bread, you don't usually talk about a dozen loaves of bread, because why would anybody need a dozen loaves of bread, right? But a dozen eggs, that's reasonable, because an egg is smaller. An atom is even smaller, so we use an even bigger number. Okay? So, one important conversion factor that comes out of this is simply that a mole is 6.022 times 10 to the 23rd. So literally 1 mole of anything is 6.022 times 10 to the 23rd anythings. Now, most of the time, those anythings are going to be atoms or molecules. So I'll go ahead and write atoms or molecules here. Technically, it could apply to anything. 1 mole of eggs equals 6.022 times 10 to the 23rd eggs, or bagels, or whatever. But we're going to use it for atoms and molecules most of the time. Okay, so that's another important conversion factor. Okay, why in the world 6.022? Now, by the way, this says 6.022 times, or 14. I think on your exam equation sheet, it probably just says 6.022. When I say it, yeah, it's right here. When I say it, I always say 6.022. I don't add those additional digits. But like, you don't have to memorize it. It's right there. If you forget it, if you want to double check and you're on the exam, just make sure you didn't mess something up. It's right there. And maybe what's even like cooler to notice, a unit over another unit. I'm telling you right here that this thing is a conversion factor. 6.022 times 10 to the 23rd. It says particles here. It's because it could be anything. This could be atoms per mole of atoms. It could be molecules per mole of molecules. Okay? But the fact that it has a unit over another unit, I'm telling you right there that it can be used as a conversion factor. These other things over here that we're going to get to eventually, unit over another unit, it can be used as a conversion factor. Okay, so why in the world 6.022 and not just like 10? Like, why not 1 times 10 to the 23rd or 24th? And for that matter, why 23rd and not 24? You know, most trillions, billions, all of those are in increments of 3. So why that number? So what's really cool is that when we talk about carbon and we say that 1 carbon atom weighs 12.01 AMU, by using 6.022 times 10 to the 23rd, we actually make it so that 1 mole of carbon atoms, or 6.022 times 10 to the 23rd carbon atoms, are equal to 12.01 grams. So this is like the tablespoon of charcoal, of ground up charcoal, would weigh 12.01 grams. So the number on the periodic table is unitless because it can be AMU if you're talking about a single atom, or it can be grams if you're talking about a mole of atoms. So that's the last conversion factor now. So we said up here, 35.45 AMU per 1 atom. Now we can also say 35.45 grams per 1 mole of chlorine atoms. And maybe I need to like bring a balance in here. I mean, I guess you guys are all in the lab, so you're doing things that are close to this at least. I don't know what your lab is this week. I don't keep up on that, unfortunately. I should. But like, I could bring a balance in and show you guys. Like 35 grams, that's like about an ounce. So if you think of like 1 square of chocolate, I'm thinking like dark chocolate, like a Lindt bar or something. This is my favorite, obviously. So like a square of chocolate is probably about 30 grams as far as weight. Okay, so it's a reasonable amount that on our macro scale we can measure out, we can physically hold. That's going to have, you know, a mole's worth of atoms in it, which is a ton and ton of atoms, but that's how many we need to get to the point where it's like, you know, something that we can measure out. Okay, so the reason why we have that specific number is so that these two units can be interchanged with the numbers on the periodic table. So anything on the periodic table, any number you want to look at, you can use it for a single atom as long as that number is associated with atomic mass units, or a mole of atoms if you use it for grams. Okay? So we're going to do, with the remaining time, we're going to do 2 practice problems where we apply these 2 conversion factors. And then on Friday, we will do nothing but practice problems with these. I probably need to even bring some more in, so we have plenty to do. But that's the end of chapter 2, is using this idea of the mole and applying it to individual problems. Okay? All right, so let's switch over to this. And I think since we have enough time, I want to just let you guys kind of struggle with these a little bit. Even if it doesn't feel like super intuitive right off the bat, but I want to give you time to kind of like work at them instead of just giving you the answers right away. So if you get stuck, use the method that we used last week when we were using conversion factors. What is the number and unit I'm starting with? Like, go back to those 3 questions. What is the unit of the thing I'm trying to get to? What conversion factor can I use? Okay? And thankfully, all of these are just one conversion factor in each problem. So I'll probably give you, I don't know, 3 or 4 minutes before I interrupt and, kind of give you a little bit more direction. So if you finish it up, great. If not, we'll talk through it. That's normal. It's just me. I think it's because the air conditioning is coming out next to me. Okay, so I'm just going to put up kind of the outline of these problems, and then I'll give it another minute before I put in the actual rest of the work. Okay, so your basic setup should look like this. Number and unit, this is where you have to start. There's nowhere else to start in this problem. The unit you're trying to get to is moles of aluminum. Now, if we wanted to be even more specific, we could say moles of aluminum atoms. Like, when you say a dozen eggs, the eggs doesn't need any more description. Sometimes it's a good reminder to remind yourself aluminum is an atom. I know that sounds dumb, but like when we get to moles of water, and then we talk about the hydrogen and oxygen atoms that make up the water, that can get a little bit confusing. So if it does, just say moles of aluminum atoms, moles of water molecules, just as like a reminder to yourself, okay? So then, this unit needs to go on the top, because that's the thing we're trying to get. This unit needs to go on the bottom, because that's the thing we're trying to cancel out. Okay? So we set up our conversion factor before we even know what it is we're going to use. Then we say to ourselves, do I know a conversion factor between moles and atoms? So anytime you have moles and atoms, or moles and molecules, the moles is always going to be 1, and the other thing is 6.022 times 10 to the 23rd. This is also called Avogadro's number, because Avogadro's the guy that came up with this. So let's go ahead and plug that into a calculator together. If you are using the button that says times 10 raised to the, then you don't have to worry about this quite as much, the parentheses that I'm about to say. But if you're using the multiplication 10, the raised to caret, and then 23, you want to make sure to use parentheses as much as possible, okay? Because this is a single number, not technically a mathematical operation. So let me show you what I mean. So 9.55 times 10 to the 25th. So 9.55, I can write that as times 10. Do I not have, I guess it's this one, raised to the 25th. Okay, that's a ridiculously big number. Your calculator probably won't spit out all those zeros. I think it's only because I'm on the iPad that it does that. Okay, so then divided by, and I'm going to do the same thing. Since I use the multiplication symbol for times, I actually, just to like be totally sure that this works out the right way, I should probably put each of those numbers in parentheses. Now, if you're using, no, even if you are using, if you're using the big E, like on a graphing calculator, the capital E thing that means times 10 to the, like that's the scientific notation button, then you wouldn't have to use parentheses. That's probably the only time when you wouldn't have to use that. Okay, so divided by 6.022 times 10 raised to the 23rd. So I get 159, we're going to say 158.85. So 9.55 was 3 sig figs. Multiplication division rule. I want to limit my answer then to 3 sig figs. So I'm going to say 159 for my answer. So 159 moles. That's a lot of moles. It's like 159 dozen. No, sorry. Yeah, 159 dozen. That'd be a lot of dozen of anything. So it is a pretty big number. Usually they're going to be more like single digits that we'll be working with. Okay, so 159 moles of aluminum atoms. And then the next one says convert this amount of atoms to grams. So the only way that we can get to grams is through moles, because from the periodic table, that number is AMU an atom, or grams and moles. And we don't go Googling what's the conversion between AMU to grams, because that's not something I would ever give you, okay? So it would be atoms converted to moles and then converted to grams. So we already did the conversion to moles, so we're just going to continue the calculation basically. We're going to take that 159 moles of atoms and we're going to convert that to grams. So if you want to change this question to just say convert 159 moles of aluminum to grams, that's what we're doing. It's just we've already done the atom to mole conversion. Okay, so similar approach. We have the moles of aluminum and we want grams. You put in the units, moles on the bottom to get rid of it, grams on top. And now, again, what you're trying to trigger in your brain is anytime you see grams and moles together, go to the periodic table. That's where that conversion factor number is going to come from. So those are the kind of things that I probably, not just having like a mental list of conversion factors, but I'm trying to see if I have a blank page here handy. Good. So if I have atoms and molecules, atoms and moles, I want my brain to think Avogadro's number. If I have molecules and moles, same thing. If I have AMU and atoms in a conversion factor, I want to go to the periodic table because each atom has a mass in atomic mass units. If I have grams and atoms, I want to go to the grams and moles. I want to go to the periodic table as well. If I have an English and metric, I want to go to the exam equation sheet. If I have a metric prefix with another metric, I want to go to my brain to do a metric conversion. So you're trying to trigger your brain to get used to, when I see these units together, where do I go to get that number? So in this example, I'll go back to that in a second, sorry. So in this example, I see moles and grams, so I'm going to go to the periodic table for aluminum. 26.98, and that could be AMU per 1 aluminum atom, but in this case, we want it grams per 1 mole of aluminum. So 26.98 grams per 1 mole. Right now, in the conversion factors, a mole has always been 1 in the conversion factors, okay? Not in like an answer, obviously. We'll eventually get to ones. It's probably not even until chapter 4 where moles are not 1 anymore, just with a different type of conversion factor. But for right now, it's always been 1 and some other number. Okay, if the other number, the other unit is grams, go to the periodic table. If it's atoms, use Avogadro's number, the 6.022 times 10 to the 23rd. Okay, I think that comes out to like 4,000 something. 4,289. Okay, wait, 3 sig figs. So I'm going to do 4,290. And I'll make sure on Friday when we do those example problems, we're talking about sig figs the whole time too, so that we get additional practice there. Okay, you probably have enough information. If you feel comfortable with it, you can go ahead and start on more of the homework. You probably could do all of it. Yeah. Do you want me to? Yep, this one here? Okay. Hi.
showed up a bit late today.
That's okay. Oh, did you? Oh, I
did,
didn't
yeah.
send it around. I didn't send it around.
Okay,
Yep, it's okay.
Okay.
I'll just scratch everyone's off. It's me.
I have a question.
Yes.
Yesterday, I was doing examples, and this one here, I didn't understand.
Okay. Density of something is point 48 or okay. 1.48. Okay. Find the mass of 1.5 liters. Okay, great. So let me. This is a good one. Okay. So 1.5 liters is your starting thing. And then it was 1.5 grams per centimeter cubed. Okay, so the first thing to remember is centimeter cubed is equal to milliliter. Those are the same unit. So one of these is one of those. So you can say 1.5 grams per 1 mil too. Like that's okay. So now, if you're starting with liters and you want to get, did it say mass in grams?
I don't know.
Okay, it probably just said mass, but mass in grams. So here you would go liters to milliliters. So that would be a
Okay.
metric
Yeah,
conversion. Then you would use this to go to grams.
Okay.
Does that make more
Okay,
sense
thank
now?
you. Yeah.
Yep.
Thank you.
Yep. Hey, question for me?
Yeah.
Good.
It's two questions. Like the exams that will be on 17th of September.
Yeah, next one.
Yeah. Do we have like any question about physical and chemical properties?
Yeah, yes, you could. Like, you know, maybe I give you one and say, you know, is this a chemical or physical property?
The problem is all the questions that it's related to physical and chemical properties. Is I need to translate it to English and Arabic.
Oh, my
guess,
goodness.
I mean, I understand
Yeah.
the role of chemical and physical properties.
But it's hard for you to understand, like, what is melting
Exactly.
in English or something like
So,
that.
like,
Yeah.
is there any like suggestion to me to
Yeah.
be on track? You know.
Yeah, I wonder, have you talked to like the student accommodations office? Like you have somebody that like handles international student stuff, right? I would ask them about using a dictionary. Because for my purposes, I would be fine with you using like an English to Arabic dictionary, as long as it's like a handheld one, not, you know, on your phone or
Yeah,
something. But I think I'm supposed to get like an official document that says I can let you do that. So if you talk to like the International Student Office,
Which is the global engagement.
I think so.
Yeah.
They would at least know who to direct you to.
Yeah.
They can probably give me an official letter that
I mean,
says
yeah,
like,
I mean,
this is
if
good to go.
the answers the question, it says clearly melting or something like that.
Uh-huh.
I mean, it's clear to understand.
Yeah,
I'm okay to
but I would
understand.
be okay with you having that as like just in case you need it.
Yeah,
So
okay,
yeah,
thank you so
yeah.
much.
Ask them about it, but then follow up with me on Friday or
Of
something.
course, thank you so much.
Yep.
Rose in jail first.
Yeah, my idea is this is the conversion factor.
Millisecond, yeah.
So,
So you can flip it.
yeah, because we need to this with
Oh,
this.
yeah, no, that's not right. So it would be this or, should write down here, 10 to the negative third second per 1 millisecond. So you want, this is not the same thing. So 10 to the third on top or 10 to the negative third on bottom. Those are equivalent, but in this instance, the units are flipped. Does that make sense?
I mean,
So,
why I flipped it now? Because we need to, this goes with this.
right,
From negative, when we flipped from bottom to up.
Right.
We change the minus 3
yeah.
to.
But you want the seconds on bottom, right? Yeah, so you want the seconds on bottom. So if you're gonna use this, you're right that, like, if you, let's say you wanted to go from, like, I don't know, 1,500 milliseconds to seconds. So if you were gonna do that, you would want milliseconds on the bottom and seconds on top. And you could do that as 10 to the negative third and 1, or you could do 10 to the third and 1. But you would always keep milliseconds on bottom and seconds on top so that they cancel, yeah. But 1 over 10 to the negative third is correct here, but only if milliseconds was on the bottom, which is not correct, right? Does that make sense? So you always have to make sure that the unit stays with the right number. And if you're gonna change the negative, that only works if it's staying with the correct unit. Does that make sense? Like seconds is still on the top up here. It is really, it's really confusing, and I like keep trying to make it simpler, but like, there's no way to make it simpler. There's just too many different ways that you could potentially do it. Okay, so just start with these two problems. They're at the end of the material, so we'll go back a couple slides to finish this stuff for today. But these are just kind of warm-up problems based on stuff we did last class. Oh, sorry. Turn this off.